brackets, because we know how to differentiate along a vector field using the Lie bracket. Here I'm not interested in that. I'm interested in doing it along a curve. So I wanna differentiate along a curve. I need to connect nearby tangent spaces. Nearby tangent spaces. And I need to differentiate some vector, like the velocity vector. I need to differentiate it along a curve, not along a vector field. Okay? So we need the suggestions. So given two vector fields x and y, we need to differentiate what is, these guys are vectors, given vectors, but not necessarily vector fields. So they may not be defined over all M. Defined over all M. A vector field is defined over M. So I have two vectors, because this is what I want to do. I want to differentiate y with respect to x, but x is not a vector field. This is what I want to do. Yes?
So a vector field has to be defined over the entire manifold?
Yeah.
So what's the difference between a vector field and a complete vector field?
No, its flow is defined for all time.
For the manifold.
Yeah,
For
for all time, yes. It doesn't go up like x dot equals x squared. So given two vectors, and we will scrutinize this to the end. We will try to kill it to death, hopefully. So don't worry about these things. So given two vectors, some two vectors, and I want to differentiate what is the derivative of y with respect to x. Right? We want to do that. And we need some suggestions. We need some, I mean, if somebody poses this question, I hope that mathematicians come and pose questions like this and we try to think with them. We will come up with good solutions and they will prove. So that will be a very good collaboration. But anyway, so if somebody came and gave you this question, how do you, what do you suggest? Any suggestion? How do you define, I have two vectors and I want to differentiate this guy with respect to that guy. We have some background, right? We have some tools that we learned through this course so far and before. First, try what you know. Why don't you define it with Lie bracket? What's the problem with Lie bracket? What about Lie bracket between x and y? So I will define the derivative of y with respect to x as the Lie bracket because this is indeed the Lie derivative of y with respect to x, right? So why not taking this? Let's see what's the problem. Why we should exclude the Lie bracket. So this is no because what? Because actually in Lie brackets, both x and y are being differentiated, right? It's like y is differentiated with respect to x and also x differentiated with respect to y, and I will reminding you of this identity. If I have x with respect to 1, and if you claim that this is really a derivative, a directional derivative, y with respect to x. So if I multiply x with 4 here, well, the 4 should come out. That's fine, right? If you want to get how y changes along that direction versus how y changes along 4 of that direction, it doesn't matter. You just scale it by 4, right? And the problem, which indeed the case, but the problem when you have a function here, well, it's the same. You should scale it by the function. You should indeed get the following. You should get the function multiplying x and y, right? It doesn't matter because it's a scalar. At the end of the day, it's a scalar. It's just a number multiplying the entire vector. Okay, x. But for Lie brackets, this is not the case. You have y because as well as x acts on y, also y acts on x. So if y acts on here, it will act on f as well. So you need to add the product rule here, that is the lead derivative of f along y. This is just a scalar in the direction of x. So this is not the way a directional derivative behaves. What I'm trying to say is that we're looking for the derivative y with respect to x. So in this case, if I have this x is multiplying by a number, it should come out and there is no additional term. You see the problem here? Both vectors are being differentiated. I'm not interested in that. The lead bracket is a very special way of doing the derivative. It was useful in some sense, but it's not a directional derivative. Okay? And to convince you more, I'll give you another reason to exclude the lead bracket. So it's again no, because simply the lead bracket necessitates two vector fields. Right? It takes two vector fields and gives you another vector field, and this is why we were able to do the derivative at the beginning. And in the problem statement here, we are saying that please, x and y may not be vector fields. Well, that's fine. Extend given a vector field, given a vector, just a vector, and not like 1 and 0. Extended by a vector field defined everywhere such that it just matches your vector at this point. And do the computation with the extended vector, the vector field. So let's see an example which we had before, but I'm giving here in this context. So because lead brackets needs vector fields, what about extension? We can do extension. For your vector that is not a vector field, I extended by a vector field. So here is an example. Let's say I have y that is whatever, anything, some vector field that you want to differentiate. This is a vector field on R2. And I want how y, so the derivative of y with respect to this vector, 1 and 0. And I want to compute this along the x-axis, y equals 0. Okay? I want to do that. Okay, easy. So, okay, so you're suggesting now to do the lead bracket between this guy and that guy, but this is not a vector field, so you're saying extend this as a vector field. Okay, let's try to extend it. So this is, say, a v. So I'm gonna extend it, so I'm gonna say, okay, I have here, here is x1. It's anything, a and b. Now it's a vector field in R2, such that on the x-axis, so y equals 0, it will match my guy. Okay? But this extension is not unique. You can have another x2, that is c and d, everything is the same. x2 in the x-axis is 1 and 0, right? So you can have many different results. That's fine about the non-uniqueness of the extension, as long as you will get the same result at the end. I'm interested in the derivative, right? So now if you go and compute your suggestion, which is x1 with y on the x-axis, it should match x2 with y on the x-axis. Otherwise, this suggestion just go and trash it. And the thing is, they don't match. Okay? Because these guys will be differentiated, and if they match on the x-axis, the derivatives may not match. So the lead bracket really doesn't work at all. So let's close this suggestion, and let's try to find another suggestion. What about the Euclidean way? So the Euclidean way, let's say we have, I'm going to call the derivative of y with respect to x, because we're going to use it. Derivative of y with respect to x, I'm going to call it nabla x1, okay? Denoted by this. So in the Euclidean way, we have a way to compute this derivative. And just to differentiate it from what we're seeking, I will have over bar here. So this is the Euclidean way, nabla x1. Which is simply what? How do you compute this in Euclidean space? How do you compute the derivative of y with respect to x in Euclidean space? Y is a vector, x is a vector. How do you compute the derivative of y with respect to x?
The gradient of y multiplied by x.
Exactly. So this guy, gradient of, so this is the Jacobian now, right? Times the x. That's it. It's super easy. Okay? Why not doing it like this, in coordinates? What's the issue? Well, I'm going to say also no, because this way of computation doesn't transform well under coordinates. And I'll give you an example. Under change of coordinates. So example, let's see what do I mean by that? What do I mean by that? Our usual things, y negative x 0,